Have you ever pondered why time seems to fly when you're having fun but drags when you're bored? Could this be a mere perception, or is there a scientific explanation behind it? Time, it's an enigma. We all have 24 hours in a day, 60 minutes in an hour, yet it feels so different depending on what we're doing. A minute waiting for a bus feels much longer than a minute spent laughing with friends. But why is that? We're all familiar with the concept of time. We watch it tick by on our clocks, we plan our days around it, we celebrate it with birthdays and anniversaries. It dictates our lives in so many ways, yet it remains one of the most mysterious aspects of our existence. Our perception of time is an intriguing puzzle. It's not always consistent, and it's highly influenced by our activities, our mood, and even our age. As children, summer vacations seem to last forever, but as adults, years appear to fly by. But what if I told you that this isn't just about perception? What if there's a scientific reason explaining why time seems to stretch and shrink in different situations? This concept is known as time dilation, a fascinating theory that challenges our understanding of time. Time dilation is a mind-bending concept from the realm of physics, particularly the special theory of relativity. It suggests that time doesn't flow at the same rate for everyone and everything, but rather, it changes depending on speed and gravity. Sounds like something out of a science fiction movie, right? But it is very much a part of our reality. So, what if time isn't as constant as we've always thought? What if it's flexible, malleable, and dependent on factors we've yet to fully understand? It seems we're at the brink of a fascinating journey through the fabric of time. Stay tuned as we delve into the world of time dilation. Time dilation. Sounds like a concept straight out of a sci-fi movie, doesn't it? But it is a real scientific theory. Let's dive right in. Time dilation is a difference in the elapsed time measured by two observers, owing to a relative velocity between them or to a difference in gravitational potential between their locations. Now that's a mouthful, isn't it? But don't worry, we'll break it down. This fascinating concept has its roots in Albert Einstein's theory of relativity. You've probably heard about it before, but for those of you who need a refresher, this theory fundamentally changed our understanding of space and time by intertwining them into a single entity, space-time. And it's within this framework that the idea of time dilation comes into play. So, what does time dilation really mean? Well, it suggests that time is not absolute, but relative. It can move at different speeds depending on your frame of reference. This is where it gets thrilling. According to this theory, time can slow down or speed up depending on how fast you're moving relative to something else. Let's illustrate this with a simple analogy. Imagine you're on a high-speed train, and you throw a ball straight up in the air. From your perspective, inside the train, the ball goes straight up and down. But for someone standing on the platform, watching the train whiz by, the ball takes a diagonal path. The same event is perceived differently by two observers in different frames of reference. Now replace the ball with a light beam, and the path of the light with time. That's time dilation. But how can we be sure this isn't just theoretical mumbo-jumbo? Well, time dilation isn't just a theory. It has been proven through various experiments. One of the most famous experiments is the Hafele-Keating experiment, which involved atomic clocks flown around the world, which showed that time had passed slower for the traveling clocks compared to those that stayed stationary. Another compelling piece of evidence comes from the world of particle physics. Certain particles, known as muons, are created in the atmosphere when cosmic rays strike. These muons traveling near the speed of light should decay in a fraction of a second. But we can detect them here on Earth because from their perspective, time is dilated or stretched out. Mind-boggling, isn't it? But that's the beauty of science. It continually challenges our understanding of the universe and our place in it. Time dilation is not just a theory, it has been proven through various experiments, so let's venture deeper into this. What if we tell you that the faster you move, the slower time passes for you? Sounds mind-boggling, doesn't it? This is the paradoxical reality of time dilation, a concept that was given birth to by the theory of relativity. Let's dive right in and explore this relationship between speed and time dilation. For this, imagine you're on a spaceship, cruising through the cosmos at a speed close to the speed of light. You have a clock with you, and it seems to be ticking away as usual. But what if I told you that for someone observing you from Earth, your clock would appear to be ticking slower? That's right. Time has slowed down for you relative to the observer on Earth. This is because as you move faster, time dilates or stretches out for you. The faster you go, the more pronounced this effect becomes. In other words, if you were to somehow travel at the speed of light, time would stand still for you. This is what we mean when we say that speed affects time dilation. Let's bring this concept closer to home. Have you ever heard of the Hafele-Keating experiment? In the early 1970s, two scientists flew atomic clocks around the world and compared them to stationary ones. Astonishingly, the clocks that traveled were slightly behind. They had experienced less time due to their high speed. Now, before you start planning to live forever by constantly flying around the world, let me just clarify that the effect is minuscule at speeds we can attain. It's only when we approach the speed of light that the effect becomes substantial. Yes, speed affects how time passes for us. But there's another element at play: gravity. Can you guess how that might affect our perception of time? Well, that's a story for our next scene. Stay tuned. Gravity, the invisible force that keeps us grounded. But did you know it also affects how we perceive time? This is no science fiction tale, but the reality of our universe. It's a phenomenon known as gravitational time dilation. Picture this: a clock at sea level ticks slower than a clock on top of a mountain. Why? Because the gravitational field is stronger at sea level, warping time and causing it to slow down. This is an example of gravitational time dilation in action. Gravity, you see, has a profound influence on time. It's a bit like stretching a rubber band. The more you stretch it, or the stronger the gravitational field, the slower time moves. This idea comes from Albert Einstein's theory of general relativity, which tells us that gravity isn't just a force, but a curvature of space-time caused by mass and energy. Here's another way to think about it. Imagine space-time as a trampoline. If you place a heavy object in the middle, like a bowling ball, it will create a dent, or a gravity well. Now if you roll a marble towards the bowling ball, it will take longer to cross the dented area than it would the flat surface. This is similar to how time slows down in a strong gravitational field. In fact, gravitational time dilation isn't just theoretical, it's been proven. Scientists have compared atomic clocks at different altitudes and found that time really does tick slower closer to Earth's surface, though the effect is minuscule in our everyday lives. So gravity doesn't just keep us grounded, it shapes our perception of time itself. It's an integral part of the cosmic dance of space and time, influencing how we experience the universe around us. Just as a river's current changes with the terrain, time too ebbs and flows with gravity and speed. Science fiction often portrays time dilation as a pathway to the future, but how does it work in reality? Let's dive into some real-world examples of time dilation. You see, time dilation isn't just a concept reserved for the realms of theoretical physics or the plot lines of interstellar adventures. It's happening all around us, every day. Let's consider GPS satellites. They orbit the Earth at high speeds and experience less gravitational pull than we do on the surface. According to Einstein's theory of relativity, both these factors influence time. The result? The clocks on these satellites run faster than clocks on Earth by about 38 microseconds a day. It might not sound like much, but without correcting for this time dilation, GPS systems would be off by about 6 miles a day. So every time you use your GPS to navigate, you're experiencing the practical implications of time dilation. But how do we know this isn't just theoretical mumbo-jumbo? Well, we've tested it. One of the most famous experiments demonstrating time dilation is the Hafele-Keating experiment conducted in the 1970s. Physicists Joseph Hafele and Richard Keating took 4 extremely precise atomic clocks, kept 2 on the ground, and put 2 on commercial airplanes. They flew the planes around the world, one heading eastward, the other westward, and compared the times of the airborne clocks to those on the ground. The result? Just as Einstein predicted, the time on the moving clocks was slightly but measurably slower. Another compelling example of time dilation in practice is seen in the lifespan of subatomic particles called muons. Muons are produced high in the atmosphere by cosmic rays, and they decay into other particles in about 2 millionths of a second. Considering the speed at which they travel, most muons should decay before reaching the Earth's surface. However, we detect a significant number of muons at sea level because for the fast-moving muons, time dilates, and their short lifespan stretches long enough for them to reach us. Still think it's all science fiction? Let's bring it even closer to home. When you take a step, your foot on the ground is ever so slightly younger than your head. Why? Because it's closer to the Earth and experiences a stronger gravitational pull. Remember, gravity affects time. This difference is minuscule, of course, but it's there, a tiny testament to the reality of time dilation in our everyday lives. These examples show that time dilation is not just an abstract concept, but a measurable phenomenon that has significant practical implications. It's not just about traveling to the future or the past, it's about understanding the fundamental nature of the universe we inhabit. Time dilation is more than just a theory, it's a fact of life, subtly influencing our everyday existence. Time dilation is not just an obscure scientific concept, it has some profound implications for our understanding of the universe. Let's start with space travel. Time dilation has significant implications for interstellar voyages. Imagine astronauts embarking on a journey to a star system light years away. If they travel at speeds approaching the speed of light, they would experience time more slowly than the people left behind on Earth. So, when they return, they might find that while they've aged only a few years, decades or even centuries have passed on Earth. This leads us to the second implication, aging. Time dilation has the potential to change our understanding of aging. We all grow old at the same rate here on Earth, but what if we could slow down that process? If we could travel at near light speed, we could theoretically live for hundreds of years, while only aging a fraction of that time. It sounds like science fiction, doesn't it? But it's a concept grounded in the reality of time dilation. Lastly, let's consider the implications for our understanding of the universe. Time dilation forces us to reconsider our perception of time as a constant, unchanging entity. It suggests that time is not universal but relative, dependent on speed and gravity. This concept is a cornerstone of Einstein's theory of relativity and has fundamentally reshaped our understanding of physics and the universe. The implications of time dilation are both mind-boggling and humbling. They remind us that our understanding of the universe is constantly evolving and that we have so much more to discover. Time dilation challenges us to question our perceptions and to explore the fascinating complexities of our universe. Time dilation opens up a whole new perspective on our existence in the universe. It shows us that time is not a fixed entity but a fluid concept. Time dilation brings us to the tantalizing possibility of time travel. Could time dilation be the key to traveling through time? Now let's unravel this a bit. In the realm of science fiction, time travel often involves hopping into a souped-up DeLorean, or stepping through a portal to emerge in a different era. But could time dilation, a concept grounded in the hard science of Einstein's theory of relativity, be our ticket to journeying into the past or future? Time dilation tells us that time ticks at different rates depending on your speed and gravitational field. The faster you move or the closer you are to a massive object, the slower your clock ticks relative to someone who is stationary, or further from the massive object. So, theoretically, if you could travel at near-light speeds or hang out near a black hole, you could slow your clock enough to leapfrog into the future. You'd age slower than everyone else, and upon your return you'd find everyone else has aged more rapidly. In a sense, you've traveled into the future. But what about the past? That's where things get tricky. While Einstein's theories allow for the possibility of wormholes, shortcuts through space-time that could theoretically allow one to go back in time, these remain purely theoretical. The energy and technology required to create and stabilize a wormhole, if they're even possible, are far beyond our current capabilities. And even if we could create a wormhole, there's the pesky issue of paradoxes. What happens if you go back in time and prevent your parents from meeting? This is known as the grandfather paradox, and it's a brain twister that has no satisfactory resolution in current physics. So, while time dilation might allow for some form of time travel into the future, the past seems to be firmly closed to us. For now, at least. Time travel remains a fascinating possibility, an enigma wrapped in the mysteries of time dilation. While we may not be packing our bags for a trip to the dinosaur era or the distant future anytime soon, the exploration of time dilation and its implications continues to captivate us. Our journey through the labyrinth of time dilation is coming to an end, but the exploration of this fascinating concept is far from over. We've navigated the winding paths of time, witnessing how it doesn't abide by a one-size-fits-all rule. Instead, it stretches and contracts influenced by speed and gravity. We've dived into the heart of time dilation, a phenomenon where time, as observed by two different observers, doesn't always match up. It's a dance of perspectives, a ballet of relativity. We've seen how speed affects time, making it tick slower for an object moving at high velocities. A trip to a distant star might feel like just a few years for a speedy astronaut but would be decades or even centuries for those left behind on Earth. This is no science fiction but a reality confirmed by experiments in the very GPS system that helps you navigate your daily commute. Then we've descended into the gravitational wells of massive objects where time drags its feet. Near a black hole, a minute might stretch into hours, days, or years. This is not mere speculation, but a prediction of Einstein's theory of relativity, glimpsed at in the cosmic dance of stars around black holes. The concept of time dilation has profound implications. from the way we navigate space to the potential for time travel. It challenges our everyday perception of time as a steady, unchanging backdrop to our lives. Instead, time is a dynamic entity, its rhythm changing with speed and gravity. The exploration of time dilation doesn't stop here. It's a journey that continues with every new discovery, every fresh insight into the workings of our universe. As we continue to probe the depths of space and the nature of time, who knows what new wonders we'll uncover. As we part ways, remember this: time is not just a ticking clock. It's an ever-flowing river, sometimes swift, sometimes slow, shaped by the forces of speed and gravity.